Hello and welcome to this Revision Monkey video on what's going to be in the 2022 exam. This video is about the required practicals that they've told us to focus on for Chemistry Paper 1, and it's for those pupils studying AQA Combined Science, and it's the trilogy version of Combined Science, which means you do 6 exams at the end, all of which are 1 hour and 15 minutes long. And this video is if you are doing higher tier. If you're not sure if it's the right video for you, then do check with your teacher before you watch it. Do keep an eye out in the descriptions as well, because I'll try and add some questions in there for you later on, and I'll also put a link to the content for Chemistry Paper 1 that they've told us to focus on. But this video is going to cover the required practicals, and those that they've asked us to focus on are salts, electrolysis, and endo and exothermic reactions. Salts required practical. So, if you react an acid, like hydrochloric acid, with a base, you will make a salt plus water. Now, in this case, the base we're using is copper oxide, and we're adding it as a solid, which indicates that it's probably an insoluble base, which it is, which means it doesn't dissolve in water. So we can't make it into a solution and add it, we add it as a solid itself. We're going to add that to acid, and the salt that we make is this, it's the copper chloride, and this state symbol here means it's aqueous, which means dissolved in water. So if we wanted to make copper chloride, we need to identify that the acid we need was hydrochloric acid, because they make chlorides, and suggest a sensible base like copper oxide to react it with. So the first thing that you do for this practical is measure a fixed volume of hydrochloric acid, for example 50 ml, using a measuring cylinder, and add this to a beaker. To that beaker, using a spatula, you would add copper oxide, but the important thing is that you would add it in excess, which means you keep on adding the copper oxide until no more will react and you have excess in the solution. You will notice when you have excess in your solution, because if this is our acid here, you will see that there's lots of copper oxide or whatever base you're using that has not reacted. So we need to get rid of that. So the next step of our process is to set up a funnel with filter paper and place this in a conical flask. We will then filter the mixture, so we will pour our mixture in here. The excess base that we don't need will collect in the funnel, and then we will be left with our solution at the bottom. We will then pour this filtrate that we've got here into an evaporating dish on top of a gauze and a tripod with a Bunsen burner underneath. And we will heat gently from underneath using a Bunsen burner, allowing some of the water to evaporate. Because if you remember from the equation above that we've just had, what we are going to make is copper chloride and water. So we need to get rid of this copper chloride, this water, in order to get the copper chloride crystals on their own. So what will happen is some of the water will evaporate on heating, but what you don't want to do is let all of the water evaporate so it actually goes dry. You don't want to get it to that stage. You want to get it to that stage where you're going to have a little bit of water left in the evaporating dish. So then our final step is to remove this evaporating dish from the heat and place somewhere warm for the rest of the water then to evaporate from the dish, and that will leave just our salt crystals behind. If you didn't leave it to evaporate slowly at the end, you wouldn't get the crystals forming like you want. Okay? In your method as well, you can describe this part of the process as crystallization. Something that I'd like you to look out for is a question on this practical, similar to one here, which says a student wants to make copper sulfate crystals. She adds some calcium carbonate to nitric acid. She then heats it gently until all of the liquid evaporates. Write an improved method for this investigation. So the thing I want you to look out for is whether they're reacting the right things together. Because you can see that they want to make copper sulfate. So for this you are going to need sulfuric acid, and they have wrongly used nitric acid. And for the copper, you will need some sort of base that has copper in it. For example, you would have probably got the marks if you just said copper itself as a metal reacting with it, or if you'd put copper oxide or copper hydroxide or something like that. Really the best thing that you'd want would be copper oxide. However, they won't penalise you if the thing that you react together does make copper sulfate. So you might have even put copper carbonate or copper hydroxide or copper something like that. So that's what you need to look out for. They've wrongly said that they're going to use calcium carbonate. And then clearly the other mistake that they've made is saying that heat it until all the liquid evaporates, which hopefully you've picked up now that you need to filter it before you do that. So you discuss how you'd set up the filter paper in the funnel and the conical flask, and then you talk about not evaporating all the water but leaving it to evaporate slowly at the end. Okay, so look out for that kind of question in the exam. Electrolysis required practical. So I think it helps by reminding what electrolysis is, and it's lysis, which is splitting using electricity. So practical people find quite difficult. Let's think about what we might want to split up. For example, if we've got a rock with a metal in it, for example, lead bromide, we might want to split that rock up so that we can get our lead out to make various things with it. Now, whilst it's a solid, the ions cannot flow, so you can't split it up. So what you'd have to do is either heat it up so it's molten, or you'd have to dissolve it in water, if it will dissolve, to make a solution. Now, with regards to your required practical, it's this one here that we're concentrating on. Okay, so when a substance has been dissolved to make a solution, not when a substance has been heated up to become molten. So we're going to look at a couple of specific examples. We're going to look at different salt solutions. In your exam, they might give you different ones to these again, but hopefully if we go through the rules, you'll be able to work it out. So this is one salt solution. So this is sodium chloride, which has been dissolved in water to make a solution, hence it's aqueous. Now, within that solution, there are certain ions. There are the sodium ions, and if it helps, whatever comes first is the positive bit. Okay, so sodium ions and chloride ions. And because it's been dissolved in water, there are two extra ions that we need to be aware of. The water itself splits up into H+ hydrogen ions and OH- hydroxide ions. So there's 4 ions which are represented down here: Na+, H+, Cl-, and OH-. The liquid down here is called the electrolyte, and the things in the top, there's one positive and one negative, and they're both called electrodes. Now, what's not shown is the fact that these are connected up to some kind of power supply, hence why they're positive and negative. So electricity splitting up the ions in this solution. In terms of charges, opposites attract. So positive ions will be attracted to the negative electrode, and negative ions will be attracted to the positive electrode. But what makes it difficult in your required practical is that because it's in solution, you have 2 positive ions and you have 2 negative ions. So what you need to work out is which one will actually go to the electrode. So these are the rules that we need to be aware of. The rule at the positive electrode, so here first of all, is that if a halide ion, which is group 7, so if anything from group 7 is there, and you'll get your periodic table to help you, that will go to the electrode. If not, oxygen is produced. So we look at the two negative ions, they are chloride and hydroxide, and we ask the question, is there a halide ion present? Now yes, there is. The chlorine, or in this case the chloride ion, is a halide ion. Chlorine is in group 7, so its ions are also called halide ions. So this is attracted to the positive electrode, and chlorine, like many other gases, go around as Cl2. So chlorine gas will be given off at the positive electrode. If that wasn't there, oxygen would have been produced. Now at the negative electrode, the rule is the least reactive element will go to the electrode. So these are the two that we've got. We've got sodium ion and hydrogen ion. We need to know our reactivity series for this practical. So out of these two, hydrogen is the least reactive, so that goes to the negative electrode and again goes off as a H2 molecule. And the sodium will stay in solution, and that will react with the hydroxide that's left over and make sodium hydroxide. Okay, so the products we've got is hydrogen coming off at the negative electrode, chlorine coming off at the positive electrode, and sodium hydroxide just remains in the solution. We're going to look at a second example now, but we're going to apply exactly the same rules. This is the electrolysis of copper sulfate solution. So it's aqueous. And the ions that you have present are copper, don't forget the first thing's positive, so copper and sulfate. And then you've got the ions in water, H plus and OH minus from the water. So again, you've got two things that you need to decide from and predict what will go to the electrodes. So let's start off with the positive electrode. Again, we said if a halide ion from group 7 is present, that will go to the electrode. If not, oxygen is produced. So we have a look at these two. This is a sulfate ion. This is not from group 7. And hydroxide is not from group 7 either. In fact, there's two different elements in each one. So oxygen is produced, and it's because the hydroxide ion goes to the electrode and oxygen is what is given off. For the negative electrode, the rule is the least reactive element will go there. Now in this case, we look at the two ions again, and in fact copper is less reactive than hydrogen. So in this case, it is copper that is produced, which will collect as a solid around the electrode, making the electrode a lot heavier. And eventually that will be taken out and replaced, and the copper will be used for pipes and things like that. So slightly different example in this case, these two will remain in solution. And really, if we know our reactivity series, when we're talking about the positive ions, a lot of the time it will be hydrogen produced, because many other metals are more reactive than hydrogen. Things that are less reactive than hydrogen are things like copper and silver. Okay, so if you see those in solution, then those will go to the electrode. If not, hydrogen will go there. If you're doing foundation, you can skip this little bit, but if you're doing higher, you also for these required practicals need to be able to do the half equations at the electrode. So let's start off with the sodium chloride solution example. We said at the negative electrode that hydrogen was going to be formed. So to write the half equation, we need to turn the ions into atoms. So hydrogen ions will gain electrons and turn into hydrogen molecules. But because there's 2 there, we need to balance it up by 2 there, which then gives us 2 electrons needed. At the positive electrode, we said that chlorine, because that's group 7, will go there. So there's a couple of way rounds you can write this. You can write it as chloride ions lose electrons and turn into chlorine, all balanced up, two of those. Or you may well see in the exam, or you can write it as if you prefer, that chloride ions turn into chlorine and give away 2 electrons. So either way round is completely acceptable. And for the next example, at the negative electrode, we said because it's less reactive, copper goes there. So copper ions need to gain back 2 electrons and turn into copper atoms. And at the positive electrode, this is the difficult one, because the hydroxide turns into oxygen, but you've got to sort out where that H goes. So the hydroxide ions give away electrons, I'll write them on the other side, they turn into oxygen and water and give away electrons. Okay, so hydroxide ions turn into oxygen, we know that bit. We know that they have to give away electrons, and this is the extra little bit. Okay, water is also made as well. So to balance that up, we need a 4 there, a 2 there, and a 4 there. Exothermic and endothermic required practical. First of all, let's remind ourselves what an exothermic and an endothermic reaction mean. With an exothermic reaction, heat is released into the surroundings. That causes a temperature increase. And with an endothermic reaction, heat is taken in from the surroundings, causing a temperature decrease. So for this practical, rather than using a beaker, we use a plastic or a polystyrene cup, because this is a really good insulator, so it reduces heat transfer, because we want to measure an accurate temperature change. So in the reaction, to get the temperature change, we're going to measure the temperature after and take that away from the temperature before. Now if it's an exothermic reaction, like I said, that'll be a temperature increase, and if it's an endothermic, we would see a temperature decrease. So we would put one of our reactants inside the cup, and then we would use a thermometer to measure the temperature before. That bit's done. Then we will add our second reactant in, like so, and we will measure the temperature afterwards. And what we normally do is measure the highest temperature that it reaches or the lowest temperature that it reaches, depending on whether it's an exothermic or an endothermic reaction. Now, this is all very well, however, a lot of heat can escape. So what we need to do is we need to insulate the beaker, the polystyrene cup. And look out for this in the exam, they'll talk about how you improve the method. So you could, for example, put it inside a beaker of cotton wool. You could absolutely put a lid on it, perhaps with just a small hole for the thermometer to go through. Those two things are really important. So in the exam, you could just be asked to set up an experiment like this to determine whether a reaction is exothermic or endothermic, or you could be given a particular independent variable that you need to change, for example, the mass of one of the reactants, or the concentration of one of the reactants, or something like that. So I'm going to go through with you a step-by-step example whereby we're going to change the concentration of an acid and see how that affects the temperature change of a reaction. So we can measure 50 ml of a 0.1 molar hydrochloric acid using a measuring cylinder and add this to the polystyrene cup. We need to measure the starting temperature of the acid using a thermometer. Insulate the cap by wrapping it with cotton wool and placing a lid on the cup. Add a 3 cm length of magnesium, for example. to the acid and observe the thermometer. Record the highest temperature the reaction reaches, and repeat this for the following concentrations of acid. Make sure you list them in the exam, for example 0.5 molar, 1 molar and 1.5 molar, and repeat the whole investigation 3 times and calculate a mean temperature change for each acid concentration. And you should find that this one is an exothermic reaction. So with our concentrations of acid, this is what we are changing. This is our independent variable. We're measuring the highest temperature that it reaches. This is our dependent variable. And we're going to use the same length of magnesium each time, the same volume of acid. So these here are going to be our control variables, and we're trying to make our results more accurate by insulating the cup.